My name is Jonas Karlsson, and I'm very happy to host Peter Boncz here, who is an old colleague and friend from Amsterdam at CWI. And we spent a lot of time discussing databases, how to store data, and so on. And one of the interesting things in Monet is that it stores data column-wise instead of horizontally partitioned. And I'm going to give Peter here a proper introduction with his own brag sheet. Peter Boncz is specialized in engineering database systems, has designed and implemented multiple database kernels, both relational and XML lately, and inclusive query processing, transaction management. His unique technical expertise is insight into the interaction between high-performance data management and computer architecture. So it's really low-level stuff, and he gets it working. And his goal, according to our discussion at lunch, was to make the CPU full and get the most out of the I/O. He obtained his PhD at the University of Amsterdam on column store database architecture called MonetDB. And he spent some years using this system for a real-time marketing analysis applications in a data mining startup, which he was one of the founders of. His company has since then been acquired by SPSS, and Peter now is a research scientist at CWI. And without further ado, here's Peter.
Okay, thank you, Jonas. It works. Okay, this afternoon I will be describing MonetDB X100, a very fast column store. This is an overview of a project that has been running for more than 3 years now. And one of the other principal persons involved in that project is in the room. It's Marcin. He's my PhD student in Amsterdam. So I'm actually doing his job now, giving an overview of this project. Which also I will cover basically everything we have done. And I hope it will fit in 15 minutes. So this is my plan. I will first talk a bit about the big background of the project. So like Jonas said, I did my PhD before. And on MonetDB, which is this column store. And now there is this new thing called X100. And I will talk about the motivation, how we went from the one to the other. The principal idea about in the X100 project is to do query processing in a factorized way, and I will explain what that means. And I will give some examples. We started out by focusing, like Jonas said, on how to do computations and relational queries really efficiently. Making the CPU fully occupied and getting most out of it on problems like data warehousing. TPCH is for us an important benchmark. But we soon found out that we had been so successful in creating CPU-efficient database engine that it, on any hardware that we could afford, it was totally I/O bound. So then we shifted focus a bit to improving I/O throughput to the system. And there are two techniques that I will present, lightweight compression and cooperative scans, that are aimed at this. That's mainly it for the talk. I will then wrap up. So, well, database, I like database systems. I'm a database researcher. Database bring you very, well, sometimes nice features like some abstraction of the problem you're articulating and how it's physically stored and how your queries are eventually, the strategy that's being used eventually to solve your queries. And you can and the query optimizer that helps or does this automatically in a hopefully nice way. So there are a number of goodies on database systems. However, we also know that in certain application areas, people tend to hard code their applications anyway. They choose not to use database systems, and one of the reasons they sometimes do that is because they feel that database systems are slow. One particular field where this happens is information retrieval. So if you look at IR systems, they are typically hard-coded management of inverted list data structures. So, and people have tried to use database systems, but then they found out that they were slow. So actually, at the core of database let's say, what databases are used, data warehousing. There's the TPCH benchmark, which models a large commercial data warehouse. And I just ran one query, the first query, which is a simple query, but it does a lot of the data manipulation. It selects 98% of the largest table, which can be hundreds of gigabytes or even terabytes large, depending on how large you scale a data warehouse. And it aggregates, it computes all kinds of aggregates. I ran this on two database systems, MySQL and a database that I cannot name because of the restrictions in the license. And on the 1 gigabyte dataset, it takes about 26, 28 cycles to run that query. And just for the fun of it, I hard-coded this particular query in a program, in a C program. And I must say I was a bit shocked when I discovered that the difference was, I mean, I was expecting a difference, but that it was 2 orders of magnitude of performance. Yeah, that's kind of significant. So yeah, this research is not maybe about finding new algorithms that change the complexity of our problems, but it's about wondering what is this big constant of a factor 100 there, and can we do something about it? And if we can get one order of magnitude out of there, that would already be a success. Okay, actually so the MonetDB work in general has been targeted at efficiency, and but people usually perceive it, like also Jonas announced me, as, well, this is a column store. So well, why do people do column-wise storage? Well, in certain situations where you have tables with many columns and you only really your application is using a few of them, then yeah, you can save a lot of I/O volume by doing column-wise storage. And that's obviously true, but it was not the motivation for using columns in MonetDB. Actually, it was different. So this is, of course, it remains true, but the main reason was, well, we had this idea of having so we had the goal of removing the interpreter from a database architecture. That was the experiment in MonetDB. So one of the reasons why maybe databases are a factor 100 slower than a hard-coded program is that they use an interpreter to interpret a query. So one way to get rid of it is to what I call, let's say, the risk approach to database algebras. To have an algebra that is so simple that it can actually do without any interpreter. Meaning it's so simple there is no degree of freedom. Every operation is hard-coded. And to make operations hard-coded, you actually have to remove all those degrees of freedom, one of them being the record layout. So if you have a model where you say, my operations only accept arrays, simple arrays, they don't need to know, they only need to see those arrays that you're passing into it, and they don't need to interpret which column from that table to fetch, etc. So I'll give an example how things work in MonetDB. So here you see indeed a column store. So there is a table with an ID, a name, and an age. These 3 columns are related by position. So that we call this a virtual OID, a void. Also indicating that this column is not really stored, the gray one that relates them. So there are basically 3 arrays there, physically. Okay, the query is I want to do some computation over people with an age larger than 30. So in MonetDB, it works like this. So you have this very simple algebra that does one column at a time. So here there is this select operation that selects all values in a column bigger than 30. And then there is the minus between square brackets, which just processes one entire column and it produces a new one with a subtraction. And yeah, so there is we don't actually need to tell which column to operate on and what is the expression, because the expressions are very simple. They do one thing. So that's what I meant with a hard-coded, very simple operator. And you can see that there is no interpreter involved. In fact, if you just look at the code of the select, it's something like this. Okay, so it is a loop over a table, a tab array, and it's just, yeah, just the job in the simplest way possible. And the simplest way possible is nice because CPUs like that. They can really, there are no abstractions, there are no APIs that are to be traversed. There are, the dependencies are clearly visible, and there are a few of them between data and control. And compilers, they can do very well with these loops over arrays, so that's what they are actually optimized for. So in efficiency, this algebra can achieve things that an interpreter would not normally achieve. However, there is a disadvantage of this approach, which is materialization. So the red thing is our result, but in between we had to materialize intermediates. And well, that is the thing that MonetDB does. So and this is the final result. So you get a 3-column table out. Again, vertically fragmented. Of everything is always vertically fragmented in this thing. Okay, so that was how it works. And it can be quite efficient, but it's kind of a pact with the devil. So I want high efficiency, and I got it. But the devil took scalability from me, because the price I paid was materialization. So, and this is still true for MonetDB. MonetDB it has this limitation. However, it did work. I mean, in this particular query, MonetDB scores 3.7 seconds, and it's well ahead of other relational implementations. It's definitely more efficient. So MonetDB is still out there. It was my PhD topic. It's now open source. You can download it. MonetDB.cv, I don't know. It speaks SQL and XQuery. Okay, but this was kind of the prelude. So the question that I had is, well, can we actually do without this devilish pact? Can we get high performance without materialization? Okay, let's first look at how our relational engine is typically organized. So here we see again a query that looks a lot like the query we had before. Now age bigger than 25. So we see here 3 relational operators. So those operators are direct implementations of the relational algebra. We have a scan that scans a table from disk, supposedly. A selection operator and a projection operator. Each operator consumes tuples and it outputs tuples. It uses usually an iterator interface. So open, next, close. So each time you call next, top-down driven, it tries to produce a next tuple by calling next on the children of the operator tree. Okay. Inside those operators, typically you have expressions, and expressions like bigger than 25 or times 0.19. They map down in the end to things we call primitives, primitive methods that manipulate individual data values. So they provide the computational functionality of the interpreter, of the database engine. So this you find in any implementation. So in MonetDB X100, so in the X100 system that we started, you see here like vertical gray areas, which are not single values, but vectors. So actually the main idea here is what we call a blocked iterator approach. So this is an iterator approach where you do not pass tuples around, but you pass vectors around. A very simple idea, but it's highly effective, as we'll see later. So it means that all the lower level APIs of the database engine are expressed not in terms of single values, but in terms of vectors of values. Okay. So a vector contains multiple data from multiple tuples, and all primitives that you execute, like multiplication or comparisons, they are so-called factorized. So they operate on an array rather than on a single value. Okay, so again here we use single arrays, and you can say, well, they are like vertical slices, a vertical fragmentation of your tuples. It's good to understand that this particular representation is not chosen because for data layout. It may happen for some situations to be a good data layout, but the main reason why we do this is to make the primitives oblivious of a record layout by just telling them about the arrays that they're actually going to process. Okay. As a side, I mean, this vertical layout sometimes is nice. For instance, it is very nice for SIMD if you have a primitive that multiplies an array, nowadays a good compiler will use SIMD instructions and it will accelerate your primitives by a factor 4, probably. So again, we have this same pattern of code that is nice for the compiler. There are also special factors, which we call selection factors. So the representation may also be a selection of vectors. So where not all tuples in the array, where not all entries in the array actually participate anymore. The selection factors are used to avoid copying. So basically, the model is arrays with data in there and a selection factor that identifies which data is still relevant. And this way, the data flows through the pipeline. So in the X100 system, we kind of break this pact with the devil. We have still our factorized primitives that look very much like the algebra that was in MonetDB, but now it's embedded in a pipelined query engine that does not necessarily have to materialize intermediate results. They can be streamed through the pipeline, just like any other database system does. Okay, and this simple idea is highly effective. It's actually strange that nobody, or that this is not done more, I would say. And it gets guesses without any specific effort very near to the efficiency achieved by my hand-coded implementation of this query. Okay. So this was done after a year of work, and but that was not the end of the story. Okay, so something we worry about is making good use of computer architecture. So currently we have to take into account that there is a memory hierarchy. There is not only disk and RAM, there is also CPU cache that you may worry about in your access patterns. And if you map that on the X100 architecture as it should be, then you can think of the vectors as being the red stuff which is in the CPU cache. Okay, there is a buffer manager. What's traditionally the buffer manager is actually a real layer lower than the layer that you can actually process data. So it's actually in a position where we wouldn't in the past have considered the disk to be. It is a real feed to get data from your memory to your CPU cache. That is the blue stuff, and far, far down we have a green disk storage. And MonetDB X100 is a system that does assume that it operates on problems that are significantly larger than memories or disk-based problems. So this is also important. Okay, so the vectors, this vertical stuff is the in-cache in the CPU cache representation, but we may choose to have our data in totally different layouts in memory and on disk. Another thing is that all vectors together should be tuned to fit the CPU cache. Okay, so if you make those vectors too large, they will not fit anymore. You will start to have cache misses because of that. The query optimizer can look at the queries that are in execution and actually figure out how many vectors queries are using and tune the size of the vectors. Okay, and here is what on the x-axis. It's again the same query of the data warehousing query, where we do this experiment on the horizontal axis. We vary the size of the vectors. In this particular data size, which is not large, it's the 1 gigabyte TPCH. This table has 6 million tuples. So on the right-hand side, we use vectors that are the entire database column, basically like MonetDB would do, column at a time. And on the left-hand side, we are doing what relational systems are usually doing, tuple at a time, one value at a time. Okay? And I also plotted this other results, the MySQL and the hand-coded program. You see them in there. So what's happening here is that as the vector size is increased from 1 to, let's say, a couple of hundred, sorry? From 1 to a couple of hundred, one effect is that if you're doing processing by the 100 tuples, the number of function calls your interpreter is doing is reduced by a factor 100. Okay, so way less iterator next calls and way less primitive function calls. So way less interpretation overhead, and it's really amazing, how far this goes down. It goes down to some optimum. However, if the factors are increased further, performance worsens again, and this is caused by the fact that those factors are too big to hold in the cache then. So you get additional cache misses because of that. So there is a clear optimum of how much data you should process at the same time. Actually, here you see a very detailed experiment where we have 3 primitives, 2 multiplication and addition, where we assume that some parameters are RAM resident in the memory, and some are already resident in the CPU cache. And you can actually see in the shape of the curve that you see so the lowest, the minimum is where data is in a cache. Okay, and there where in the green line is where is the operation, the add, that has both its operands in cache. And there you can actually see the L1 performance at 1K tuples in this case. If it becomes too big, it's out of L1, and then you are still in L2, and otherwise you go up. Okay. And finally, I talked about these selection factors. Even our query result at let's say column at a time is equal what you would get with MonetDB, so it's confirmed. But there is a difference that is because of the selection factors. So the selection factors allow you to prevent copying data after you select from it. So you see actually the difference totally explained here. So it's amazing that the performance of the X100 prototype is almost the same as MySQL with 1 tuple at a time, and it's exactly the same as MonetDB with column at a time. Okay, and translated into my previous graph, MonetDB uses column at a time, so that means that its columns are always RAM resident; they're never cache resident, so you never get this optimal performance. Okay, so this works. Like for simple calculations, it's a really simple ID, and then I'm talking about, it is not that easy to build an entire database system on the principle of factorization. You have to do some work for it. There are a number of benefits. So one of them I already talked about. It reduces interpretation overhead, less function calls mainly. But sometimes having an intermediate unit of processing data also gives you some opportunities. For instance, if you think about so some of the activities that you normally would do for every value, you can maybe do only for every 100 values. And this facility allows you to push some of your work. It's kind of strength reduction. You're pushing things out of a loop to an inner loop. So, for instance, checking whether you have enough buffer space if there is overflow. If you check if there is enough for 100 tuples, you can do the check only once in every factor. And there are tricks that you can play with that. If you do a merge join, you can check. You get a vector of tuples. You check immediately the last one. Okay. If that one is bigger than your current tuple, you can skip the entire vector without touching any of it. And in many algorithms, there are tricks you may play if you have multiple values to process. Okay, so basically what we had to do is we had to go to all the relational operators and figure out ways to encode them in a factorized way. So you can really do really weird things. So, for instance, selection. In selection, so here you see this selection code again, very simple. But what it does an if-then-else. And on modern CPUs, you have to think about, or there are these effects of branch prediction. So, so the CPU tries to execute ahead. It is so in these pipeline models, operations are decomposed in multiple stages, and they are executed in pipeline fashion. And if an Ifthenelse is found, then the CPU tries to guess which is the next instruction. It puts it already in the pipeline, but if it guesses wrong, you get a mispredict. And if a mispredict happens, the pipeline has to be flushed, results have to be thrown away, and your code runs slower. And you can actually see this happening. So if you have this very simple selection, just a comparison, and you vary the number of tuples that qualify the selection, yeah, the worst case is 50%, because then it's very hard for the CPU to guess what's going to happen. So you see this curve, this round curve, of how fast this loop runs, and at 50% it runs worse. If it's very low or either very highly selective, then it runs best. And so there are tricks you can do. You can, for instance, so the Ifthenelse is the obvious way you do it, but you can also do predication, where you transform the Ifthenelse in a data dependency. So with predication, you always, let's say, append the tuple to the result, but you increment your pointer with a Boolean, with a 0 or a 1. Okay, and then you get a constant line for that, which is better in the 50% case because there is no misprediction. And you can even do weird tricks, like, I mean, for the very low selectivities, you can, if you know that there is very few tuples qualifying, you can test multiple at the same time and have only one if per 4 and well. And this infrastructure allows you actually to toy with that, and you could dynamically choose the primitive that works best, or that works best given the current selectivity that the operator is observing. Okay, so you can squeeze some performance with that. Another thing that we have to do often is hashing. So what you have to do now is factorized hashing means that you get 100 or 1,000 values, and you have to look them up in a hash table, but you're not going to do that one by one, but you're going to push the 1,000 candidates through the whole process of hashing, so going through the bucket chain list, all step by step, all at the same time, all together. So this is an probably incomprehensible drawing that more or less tries to explain how you do that. So all these vectors, they move around. You compute for all vectors a hash value. You compute a slot number. Then you do a vectorized comparison to check whether there is a hit. And you select out those that are hitting and those that are not hitting. You're doing a next on all of them, and then you're pumping them back into the loop. So that's factorized hashing, and that's what this system does. Okay, so all these operators have some factorized equivalent. Okay, there are details to be found in papers here. There is some work at IBM that in aggregation and projection also does something they call block-oriented processing, which is related. Okay, so this was the core engine was actually completed, or we had a pretty good idea of how it would work after not too long time, only maybe a year or 2 years. But then we figured out we had a problem. So we had a really powerful prototype a query engine that could process huge amounts of data per second. So it definitely worked in memory situations. But if you have such a powerful technology, you would like to use it on large data, which is not memory resident. And then if you look at how fast this thing moves through the data, in the case of my example query, it moves at around a gigabyte per second, 900 megabytes per second. That was, at that time at least, for us definitely out of scope for the I/O systems that we have. So this system was very fast, but totally I/O bound if you would do it on a larger data set than 1 gigabyte. So feeding the beast, this thing goes very fast. There are two ideas that I will present. So one is this lightweight compression, and the other is trying to share disk scans if you have concurrent queries. So first, compression. So the idea of compression is that, well, if you store data compressed on disk, and you have a very fast decompression algorithm that is faster than the bandwidth that your disk provides, and I'm talking about the RAID disks here, even, then you can win. by loading the data in compressed form and decompressing it in memory. So in our particular example of TPCH query 1, we are looking at 900 megabytes per second. So we wouldn't have to have a decompression algorithm that runs at 900 megabytes per second. But not even that, because we wouldn't want to use all our CPU only for decompression. So let's say that we would want to sacrifice 1/3 of our CPU effort in decompression to have 2/3 over to do the real work. That would mean a decompression algorithm that runs at 2.7 gigabytes per second. Well, on that hardware, on current hardware, that's not possible with even the performance-optimized versions of normal compression libraries. They run at maximum in the 300 megabytes if you use LZO. So we invented some new lightweight compression schemes to cater for that. So the key ingredients for this new ultra lightweight compression algorithms are column-wise compression. If you think about it, our column stores and compression, they are, or column representation and compression are natural partners, because if you store your data column by column, you get data from the same distribution near each other. And that helps compressibility. If you have a record that contains widely varying distributions, it's harder to compress, at least more effort. Secondly, we would like to use the factorized approach to get high-performance decompression routines. So not one-at-a-time compression, surely. Also look very good at the properties of the algorithms. So if-then-else branches, they are to be avoided, for instance, because of this branch misprediction effects that you get. So first, let's look at what kind of compression algorithms there are. So currently we have something called P4, patched frame of reference. Actually, frame of reference was proposed by Goldstein et al. Some time ago already. It's a very simple idea. You just store per disk block, in their case, a minimum value, a base, and you just provide the deltas from that base as your value. So this works for numerical columns. So a b-bit value, very simple encoding scheme. Normal frame of reference doesn't allow any things that are outside the region base and base plus 2 to the power of b, but patched frame of reference does. So the idea is that you exploit the frequency, and the frequent values should be inside these encoded regions, and there can also be not encoded values in this compression scheme. They're called exceptions. Okay, P4 delta is kind of the same, but on the deltas between successive values. So this is in inverted list, you call this gap encoding, the gaps between the various postings. You find in many databases you find ordered sequences or quasi-ordered sequences where this works pretty well. So the dictionary encoding is purely frequency based. So you have a dictionary of the 2 to the b most frequent values, and you store that dictionary somewhere, and you emit a code that represents a value in the dictionary. In patched frame of reference, you can have exceptions again. Okay, so now we have 3 schemes for P4, P4 delta, and PDict. They all use the same kind of storage. So there is a forward growing in your disk block. There is a forward growing area of code words. These are the b-bit code words, the fixed length code words. And at the end of the block, growing backwards, is the section of exceptions. So those values that could not be encoded. Okay. So now the decompression. So normally, I mean, there are other column stores or other database systems that use compression. And what they usually do is they decompress as soon as the block is being read from disk. So This makes it easy to later process the data because you don't have to, the data is already ready for use, let's say, in your buffer manager. Problem is that if you do that, you're effectively crossing the boundary. So when you read, when this block is read, you're going to decompress it. So actually, to decompress it, the CPU needs that data. So the whole block is moved to the CPU cache. It processes it, and then it stores it. And it remains there in the buffer manager in your main memory until some query is going to use it. And then effectively the cache had been traversed 3 times. First you have to get all the data up, and then to store it in the buffer manager and to use it finally. So in this system we don't do that like that. We keep our blocks compressed in the buffer manager, and only when we use them, factor at a time, so 100 tupes at a time, we decompress. So this is and effectively, so we are compressing between the boundaries of CPU cache and memory, not between the boundary of memory and disk. And so you have to cross the boundary less often, and you can store more data in your memory, which is also good. So we did some experiments later where in information retrieval benchmark, the terabyte track, where this was exploited. So I mean, this system could score very well because the entire index would be memory resident. So there's a terabyte of raw data. With the compression, in the end, there's 9 gigabytes in this case of inverted lists, and that was storable on four workstations, thanks to the data compression. And you see actually that this database system is able to outpace. Was able to outpace a number of, or actually all, because it did 3.2 queries per millisecond. All of those hard-coded inverted list systems that the information retrieval people participate with. Anyway, so this is the value of also of having compression just for getting more stuff in RAM. So these algorithms, they are coded to squeeze the last cycle, and so they we are aiming for this high bandwidth that to achieve at least 2 gigabytes per second at least to be able to decompress data without really suffering the consequences or performance penalties from that from even a high-end I/O infrastructure. So if you think about it, if you want to decompress 2 gigabytes of data, it means you have only a few CPU cycles per value to decompress it. So it's really performance critical. A naive way, so I talked about compression schemes, and they all had in common that they have either values that are encoded in a small b-bit representation, or they are exceptions. And a very simple way to decompress that is to just have some kind of exception code. Okay, so if there is an exception code, you take an exception, and if there is no exception code, you decode the value. So this is this loop, but it's an if-then-else loop. So what happens if you look at the performance of that loop? It deteriorates quickly again because of this branch misprediction. So at 50% exceptions, so there is a graph here that shows what happens if there are more exceptions, and with more exceptions, it quickly deteriorates because of these branch mispredictions here in this if-then-else. Actually, we use CPU counters, and you see that the number of mispredictions can go through the roof at 50%. So there is an alternative way that you can actually do this. And we call this patching. So that's why all these schemes are called patched compression schemes. So instead of storing exception code, we store a value there, but we know that this value here, because it's an entry point, it is actually an exception. Okay, so the fourth value in this block, fifth value, the 3, 1, 4 is P. Should be 9, but it says 6. So it's an exception. So we take the first exception. Okay, so you would emit 9 here. And the 6 says that in six steps from there is the next exception. So it's actually just a linked list. So we use the B bit values as a linked list. Okay, so this is how it goes. So one further. Okay, so you follow the linked list. By following the linked list, you can patch up the value sequence. So the algorithm is real simple. So first you just go through the data and you decode it as if all the values were good values and no exception values. And you emit wrong values there for the exceptions. And then you patch up your result. And this is actually faster. So, so then you walk the list. You walk the list only for the exception, so this loop doesn't take as many iterations. Really simple code. And then this happens performance-wise. So we really beat the simple Ifthenelse. And it gets, in the best case, to 2 gigabytes per second of decompression speed. You see the 3 different families there. Schemes. So patching makes 2 passes through the data, but it's faster because there are no branch mispredictions. Okay, so we run more queries. This is more data from the TPCH data warehousing benchmark. So if you have a slow I/O system, like we usually have, not too many disks, 4 disks per core, you are heavily I/O bound in general, and then compression translates more or less directly to performance. Okay, and you really don't suffer much. You see here, if you have more disks, this disk, I think this system had 450 megabytes per second of throughput. You sometimes win, but you don't lose, or you don't lose much at least, due to the decompression. And this system is really fast. So if you compare it with commercial numbers these are official TPCH numbers from the TPCH website. It's not really a fair comparison, I must say, because it's not. This is just a prototype, but it indicates that the raw performance is very high. You see that it beats often those numbers of a system that has 142 disks, so it has 10 times more disks, 8 times more cores. Okay, so it's really fasting. So MonetDB X100 and the compression in it is published in ICDE. There is some more work in column stores, and because, like I said, column stores and compression really go well together. And the group of MIT of Stonebreaker has done a bit of work on that as well. So I'm off to my last topic. What is my time actually? 5 minutes? Yeah. Okay, now I'll be quick. So about disk sharing, I may actually skip some of it then. So here you see some trends in disk. So before I may actually shorten it, but this is what I do want to say. So the situation with latency versus bandwidth in disks is really kind of hopeless currently. It has grown so far apart, and if you look at what database installations do, I mean, if you look at TPCC or TPCH installations where they put at least 20 disks per core, or for TPCC more, to get a balanced system. And if you think about multi-cores and what's that going to do with it, I mean, it's really not sustainable anymore. That means that as database researchers, we have to think of different ways of using disks. We have to go more sequential. And so here you see TPCH. It is very common that they just buy disks that are, or in those data warehousing configurations, they buy the very smallest disk that is available, 18 gigabytes, and then they have 140 of them for a total of 2 terabytes of storage. And we're talking about 100 gigabytes that's compressible down to 30. So does this make sense? It doesn't really make sense for me, actually. So it's kind of an unsustainable situation right now. So it will not go on like this. If you look at what you have to do, the situation versus latency and bandwidth. So here is a small experiment where you do, on the one hand, large sequential reads. So these are the thin lines. And the round lines are where you do random access. and you vary the block size. So obviously there is a huge difference if you have small block size in doing sequential or random. It's an enormous difference, really. Only when you have a random access pattern but you use larger block sizes, your performance gets more reasonable. So what is a good block size that permits you to do random access? Well, currently it's about 1 to 8 megabytes. So that is and it's rising. Each year, actually, this good block size is growing. So that's something that needs to be taken into account, really. And 4 kilobyte block sizes, they are really a thing of the past. I mean, then you can't really use them then you don't have any freedom to schedule reads. You should only use them sequentially. But so there are a number of things that you can do as a database engine to try to get more. Actually, my thesis is that databases should really focus on disk-based problems on only doing sequential access. And if you do non-sequential access, it should be bulky, like megabytes at a time access. So the things that you could do is having tables in multiple orders available, clustering tables on joins and join orders, so you have 2 tables in the same order available already, so you can do merge joins between them. Well, using column stores like MonetDB or MonetDB X100, lightweight compression, and coordinated concurrent disk, because all this gets worse if multiple programs at the same time are trying to use the disk. Then the programs are going to fight for the bandwidth, and bandwidth is even going to deteriorate, and your seek times are going to increase even. So, okay, very short about what we did with this fighting for bandwidth. So typically, I'll just go to the examples. So here you see what happens in the buffer manager when under a default policy in a database system. So so a query comes in, query 1. The red blocks are the time where it's actually waiting for data. Green is when it's processing a block of data, and blue is when the block is cached in the buffer manager. So let's suppose that we have here room for 5 blocks. So after you have read more than 5 blocks, you will swap out blocks again, so they will disappear from this trace. Okay, suppose a new query comes in. So what will happen is that there are now 2 points on the disk that are being accessed at the same time concurrently, right? And so this means that there is going to be more seek times, and actually your I/O throughput will go down. Additionally, there are opportunities that are lost because queries that need the same data are not using it from the other, because everybody wants to start at the start of your scan range. Okay, so they are doing all this I/O while they could actually reuse I/O of the other systems, of the other queries. So data is read actually many times, bandwidth deteriorates, and both latency and throughput of the system are bad. And these are the traces that are produced. So over time you plot which disk blocks are fetched, and you see multiple lines at the same time being active. Okay, so there are things that you. I will actually skip around these things. So this is elevator policy, so you can do all this scheduling stuff. An elevator, you get only one trace at the same time. You make sure that there is only one cursor going through the data. The effect is that that you get optimal throughput, but latency is bad because slow queries hold up fast queries, and short queries have to wait all the way until the elevator reaches their point. So we did some work called cooperative scans, where we try to get a scheduling policy that allows cooperative scanning that gets both good throughput, like you can get with elevator algorithm, but also gets nice latency. So I will not explain the algorithm. Let's show how it works. So suppose we have a query that comes in, but then a second query comes in. Actually, the second query has a range that doesn't overlap with the first query. But because it's a very short query, it's prioritized. So actually, this query gets its data. The other query the first query doesn't get data for a short time. But query 2 quickly finishes. Then query 1 resumes. A query 3 comes in that has an overlapping range, both with query 2 and with query 1. Okay? So the data of query 2, it sees, is still in the cache. Although it's the last data it would read normally, because at the end of its range, it starts reading that data right away. So the idea behind this algorithm is that scans accept data in non-sequential order. Okay? So it starts up there. Oh, that didn't work. Up there. With those two blocks that happen to be there, and then resumes here. And query 1 is now not accepting the blocks it would usually try to read, but it uses the blocks that are both interesting to it and to query 3. So there are two users of these blocks. Okay? And after query 3 is done, also quickly, the remaining blocks are read. Right. So you get these very strange usage patterns where there are no sequential lines anymore. But if you plot those the three, well, actually I didn't discuss attach, but you have the normal policy and the elevator policy, and the relevance policy, which is the normalization point here. And test in a wide range of different scenarios, fast queries, slow queries. Right. I'm out of time. Is this, okay. Well, I'm almost done. But yeah, I will wrap up in 2 minutes. Okay, so this adaptive policy also helps, especially if you compare it with what usually happens, the normal approach. Both in latency and throughput, you can significantly improve the way your disk is used. Okay, my conclusion. So I presented this the work that has been done in the entire X100 project. It is a new database kernel from CWI. It uses this blocked iterator model that makes it so fast. And so fast that we did these I/O optimizations to balance it more with disk-based storage. So we did lightweight compression schemes and this cooperative scheduling in the storage manager, which gets you the lightweight compression in many benchmarks, or both in IR and in data warehousing, got us a typical factor 3 of compression and also speed. And like you saw here, maybe you can win a factor 2 if you do this. In our benchmarks, we saw kind of a factor 2 both in latency and throughput of your queries with this cooperative I/O scheduling. So these things are useful techniques for the system. And we have tried this on data warehousing and also in information retrieval workloads. So there is lots of future work, and you can find more literature here. Thank you. And sorry for being a bit late.
Yeah, no problem. Yeah. All right. Thank you very much. Thanks for coming.